So first, thanks for inviting us to present our paper on shard polytopes. Thanks for the opportunity to do this remotely. Greetings to everyone in Tel Aviv and wherever in the world you are physically right now. This paper was a collaboration of Arnaud Padrol, my thesis advisor Vincent Pilot, and myself during the preparation of my PhD thesis. And unsurprisingly, for a talk or a paper about combinatorics, it starts with permutations. And it starts with permutations partially ordered by inclusion of inversion sets, which gives us the well-known weak order. To remind you, an inversion of a permutation means that there's a pair of integers such that the larger one appears before the smaller one, while the identity permutation has none. 4, 3, 2, 1 has all possible inversions. So they form this poset, and it is known that this poset is in fact a lattice, meaning that there are meets, unique maximal lower bounds for any two elements, and joins, unique minimal upper bounds. We'll be interested in all of them. And let's add some geometry to this combinatorics by looking at the Braid arrangement, which is an arrangement of linear hyperplanes. In this case, it's the arrangement of hyperplanes of the form xi equals xj for any I and j between 1 and n. And these linear hyperplanes, they split the space into regions. And each of these regions, it has some neighbors. And the union of the closures of all the regions gives the entire space again. In the Braid arrangement, in the special case of that arrangement, we can describe the regions by the order of the coordinates of all of their points. So for example, here, first comes before the third, comes before the second, comes before the fourth. And this is how we can label the regions of the Braid arrangement. But we can just label regions of any arbitrary arrangement. And if we decide on one of them to be what's called the base region, in this example, canonically, we will choose identity permutation, then we can partially order the regions of this arrangement just by inclusion of separating sets, which are sets separating one region from the base region. And in the case of the Braid arrangement, the hyperplanes do to the labels exactly what inversions do. So as the poset of regions of this arrangement, we just get exactly the well-known weak order. Let's have a look at another object that is related to both the weak order and the Braid arrangement, which is the permutahedron. And the permutahedron can be obtained from a single vector 1 through n, just by computing all the permutations of this vector, looking at them as points, and then building their convex hull. There's also another way to build it closely related with the closer relation to the Braid arrangement. If we choose for each of the hyperplanes of the arrangement a perpendicular vector, and then we build the Minkowski sum of all these line segments and translate it appropriately, what we will get is the permutahedron again. And we see that these two objects, the Braid arrangement and the permutahedron, they seem to be closely related. This is because the vertices of the permutahedron correspond to the regions of the arrangement. The rays of the arrangement correspond to the facets of the permutahedron. The edges of the permutahedron are all perpendicular to each of them is perpendicular to one of those hyperplanes. And this is because the fan of the Braid arrangement is precisely the normal fan of the permutahedron. So now the weak order is ordering three things equivalently. First of all, it's ordering permutations of the symmetric group. Secondly, it gives us an order on regions of the Braid arrangement. And thirdly, it also gives us an order on the vertices of the permutahedron. So let's just label these vertices or these regions or these permutations by numbers from 0 for the base region up to 23 to have easier numbers to work with, and look at an operation that can be applied to the weak order as well as other lattices. And that operation is called a lattice congruence, which is an equivalence relation that does preserve meet and join of a lattice, meaning that whenever we have a meet of two elements, x and y, we can replace both x and y by equivalent elements, and what we'll obtain as their meet will not depend anymore on the choice of representatives of the congruence class. The meet will always be in the same congruence class regardless of the choice of representatives. And to look at a very simple example, this is just a little diamond cut out of the weak order. We have 8, 9, 14, and 15 as just numbers of regions or numbers of elements. And in order to obtain lattice congruence, let's imagine we want to have a lattice congruence where 8 and 9 are congruent, so where 8 and 9 are glued together. Then we have to look at the join of 8 and 15. What's their join? The unique minimal upper bound, that is 15. The join of 9 and 15 is their unique minimal upper bound, it's 14. So when we build joins of one element of this congruence class together with 15, one time we get 14, one time we get 15. In order to have a lattice congruence, we need that 14 and 15 have to be equivalent as well, because we want to preserve meet and joins. So whenever we build a lattice congruence and we glue a bottom edge in such a diamond, we also have to glue the opposite top edge of that diamond. So whenever 8 and 9 are equivalent, 14 and 15 have to be equivalent as well. And of course, these conditions, this is just the most simple condition. Working our way through a lattice, we get more complicated restrictions, but this is how it works. And given such a congruence, we can now construct a quotient of a lattice by applying this congruence to the lattice itself. And what we get is what's called a lattice quotient, which is just the lattice whose elements are not the original elements anymore, but now the congruence classes of the lattice congruence we just constructed. So in our example, we did just congruence classes. One contained 8 and 9, one contained 14 and 15, while all the others remained singletons. And the order we impose on them is just the original order on L. And because it is a lattice congruence, this is well defined, and this is again a lattice. Now let's think back about geometry. We applied this to the weak order. We can apply such a congruence to any lattice of regions, and we may ask now what happens geometrically in the arrangement, because each number here is representing one region of a hyperplane arrangement. So as every element of the lattice corresponds to such a region, each equivalence class now corresponds to a connected set of regions. And what does this look like? This looks something like this as soon as the picture appears. This looks like what's called a quotient fan, which is just the original arrangement fan, but where we glued 8 and 9 and where we glued 14 and 15, the part of the wall that used to separate these two regions has now been removed. So 8 and 9 and 14 and 15, they each now are one larger region. And this is not trivial, because if we would have done this with an arbitrary equivalence relation on the lattice, we might have obtained no matter what. It would not have been even guaranteed that the region is still convex. But it's the result by reading that whenever we glue congruent regions, so we glue according to a lattice congruence, we get convex cones as our new regions, and these cones together still form a fan, still form a complete fan, which is called the quotient fan, corresponding to that lattice quotient. And we saw that for the original fan of the arrangement, we had the permutohedron, which had this fan as its normal fan. So it's natural to ask, after we applied a lattice quotient, is there still some polytope whose normal fan is now equal to that quotient fan? And this is what we call a quotient tope, a polytope whose normal fan is the quotient fan for one certain lattice quotient. And it has been found out by Vincent Pilot and Paco Santos that whenever we have a lattice quotient of the weak order on the symmetric group, so on the lattice of regions of the Braid arrangement, such a quotient tope does exist. So this is an example of a quotient tope for the lattice quotient and the quotient fan we just saw. You see here, this is where 8 and 9 were glued. Now there's just a single vertex in that region, single vertex there. And it's still, again, this quotient tope has the property that its normal fan is equal to that quotient fan. But the construction of Pilot and Santos is rather technical, and it does not generalize easily to other arrangements. So we asked ourselves, is there a better way to construct quotient topes? One way to work in this direction is to look at how this quotient tope is built. And you see that what's the difference between this quotient fan and the original fan is that this pink hyperplane that goes around here, a part of it is missing here, where 8 and 9 and 14 and 15 were separated. So let's try to describe these missing parts of the quotient fan, and we will see how we can use them to build quotient topes. So these missing parts are called the shards of the arrangement, and shards are the connected components of the arrangement hyperplanes after cutting. Now, what is cutting? Cutting is something that depends on the base region of the hyperplane arrangement. The base region determines that some hyperplanes are more important, so to say, than others. The ones that are directly adjacent to the base region are considered the most important ones, and the more the more far away they are, the less important they are considered to be. This is roughly speaking what their importance is. And then the more important hyperplanes cut the less important hyperplanes. This is a kind of a 2D example. In 2 dimensions, a hyperplane is just a straight line. So this road intersection in Tel Aviv gives you 2 important roads here and here. And these 2 important roads, they cut this less important road into 2 pieces, the piece on top and the piece on the bottom. And these pieces are now the 2 shards of that hyperplane, because the name comes from, if you think of a hyperplane as being a pane of glass and you break it into pieces, then these pieces are the shards of that hyperplane. And these shards are precisely those parts of hyperplanes that are either completely included or completely missing in a quotient fan. So these are the smallest parts that we can break a quotient fan apart into. And just as we saw that we cannot arbitrarily glue elements together in a lattice congruence, we have similar rules that we cannot arbitrarily choose shards to remove or to retain in a quotient fan. And these rules can now be looked at from the perspective of shards instead of the perspective of individual pairs of regions. And this works in the following way. By removing entire shards instead of gluing pairs of regions, it is easier to describe, and it's also easier to denote. So shards are represented here by these little arcs. As we saw, these are the shards of the Braid arrangement. The hyperplanes in the Braid arrangement are of the form xi equals xj for some I and j between 1 and n. So for example, geometrically, this the shard represented by this symbol means that it's part of the hyperplane. These can be imagined to be numbered 1, 2, 3, 4. So this one is a part of the hyperplane x2 equals to x4, and both x2 and x4 are smaller than x3. So this shard is the set of all points that satisfy these conditions. And the colors in this diagram, they correspond to the colors of the hyperplanes that I showed you in the visualizations before. So you see the pink hyperplane has 4 parts, and while the yellow hyperplane, for example, it has just 1 part. This is because it's a basic hyperplane, so it is not cut by any other hyperplane, while this is non-basic, not important, and therefore cut by all the other hyperplanes in the arrangement into 4 individual pieces. Now, what does this statement here mean? That whenever we build a congruence on the lattice of regions, we can completely describe this congruence by which shards have been retained in the quotient fan and which shards have been removed in the quotient fan. And the conditions on gluing regions of the lattice of regions now translates into the fact that whenever we want to retain one of these shards, we also have to retain all the shards that are above it in this order, which is called the forcing order. And this gives us a way to look at the quotient fan, because the union of the walls of the quotient fan is also just equal to the union of the shards that have been retained. And this is where the following observation comes into play. It's an observation on the walls of a normal fan. And when we build up a normal fan of a Minkowski sum of 2 polytopes, if we look at the normal fan of the Minkowski sum and look at the union of its walls, its wall union, then we see that nothing in the wall union of the Minkowski sum is new. Everything in that wall union has already appeared as part of a wall in one of those polytopes where the green polytope was made up from. So remember, our goal is to construct a quotient tope, a polytope whose normal fan is the quotient fan. So we want to we want to try to sum up small polytopes to get to our quotient topes, and we're allowed to do so through Minkowski sums, because if we do it in that way and we're careful in our choice of small polytopes we sum up, we will never obtain any wall we don't want, and we will also retain all the walls we had before. So if we find a smart choice of small polytopes to sum up, we can build our quotient tope and build the corresponding quotient fan step by step, just adding up walls and walls in the quotient fan until we have obtained the entire quotient fan. And for the braid arrangement, we constructed such polytopes for each of the shards. And we did so in a rather combinatorial way. We looked at this notation of a shard again. We colored the dots below the arc in black and above the arc in white, and the left endpoint black, the right endpoint white. And then a shard matching is just an alternating sequence of black and white points. We are allowed to take all 4 of them because they are strictly alternating. We are allowed to take first and last, first and second, third and fourth. Now we have, these are shard matchings. We can easily translate them into vectors by translating black and white to plus and minus 1 and not selected to 0. And these points can then be used to build a convex hull. And the convex hull of all these points together is what's called our shard polytope corresponding to that shard. And this way, for each shard of the braid arrangement, we can build such a polytope, and these will be the building blocks we use to sum up through a Minkowski sum, which we sum up through a Minkowski sum to obtain our shard polytope. And these shard polytopes do have 2 remarkable properties that are needed for a construction. And these 2 properties are, whenever we look at the polytope of a certain shard, for example, this is the polytope of the, this is the shard polytope we just looked at, the pyramid over a square. Then this polytope has 2 properties. First of all, the wall union of that polytope contains the shard itself. So in this case, that little part of pink hyperplane, which the shard corresponds to, is in the normal fan of the shard polytope. And second of all, if we look at the wall union of our shard polytope, it is contained in the union of the shards that force that shard sigma. So whenever we sum up, whenever we Minkowski sum with this shard polytope, we will add the shard we were looking for. And secondly, we will not add anything that we did not want to have in the quotient fan. Because remember, we want to construct a quotient fan, a quotient tope for a certain quotient. A quotient corresponds to an upper set in the forcing poset. And all the walls that appear here will be parts of shards that are above the shard we constructed the shard polytope for in that forcing poset. So while our construction of shard polytopes is adapted to the braid arrangement by the construction of the shard before, this idea of shard polytopes with these 2 properties is quite general, because once you are able to find a way to construct such shard polytopes for shards of a certain other arrangement, you will always be able to get the quotient topes, regardless of the combinatorial structure of the arrangement. If you have shard polytopes, then you obtain quotient topes. And we did so for the braid arrangement, leading to our main result. Whenever we have a lattice congruence of the weak order on the symmetric group, speaking differently, a lattice congruence on the lattice of regions of the braid arrangement, that one does retain an upper set of shards. And if we sum up the shard polytopes for all those retained shards, what we get as a sum of those shard polytopes is a quotient tope for that lattice quotient. So it is a polytope whose normal fan is the quotient fan containing exactly those shards that have been retained by the lattice congruence. That is the idea of a quotient tope built from shard polytopes. And all the quotient topes that were constructed by Pilot and Santos earlier with their construction are just special cases here, because it just says we sum the shard polytopes, but in fact we can put arbitrary positive weights on each of those shard polytopes. Why is that? Because if we build in the Minkowski sum, we add in a small polytope, or if we add in a large polytope, if they have the same normal fan, it won't change anything in the quotient fan of the sum. So we can scale our parts that we sum. And this way, one of these scalings gives us the quotient hopes of Pilot and Santos. They are a special case of our construction of quotient hopes. And this is because shard polytopes are rather elementary polytopes, and they are quite useful to describe stuff. For example, we can look at this illustration again that Dorian just showed in the talk before, the illustration of the space of deformed or generalized parametrahedra. It was also already known that this can be parametrized by submodular inequalities. It was known it can be parametrized by Minkowski combinations of faces of the standard simplex. But we found another way to parameterize the space through Minkowski combinations of shard polytopes. So this is for the Braid arrangement of rank 3. We get this space, and it has each of our shard polytopes is one of the vertices. Of the blue one, it's here, the red one is here, the green one is here, and this one is there. And we can also find, for example, the classical associahedron or a translate of it as the Minkowski sum of the red shard polytope, the blue shard polytope, and that shard polytope. And well, the polytopes in the interior in here, they are different shapes of parametrahedra. And in the boundary, we get polytopes whose normal fan coarsen the braid fan. And while each shard polytope is in one of the vertices, not all of the vertices are shard polytopes. Now, we went on to describe the same kind of shard polytopes also in a different type of arrangements, because, well, our construction of shard polytopes saying they have to have two conditions. They have to contain the shard. They are not allowed to contain anything that's not forcing that shard. And this allowed us to look at another arrangement, which is the arrangement corresponding to the weak order on the hyperoctahedral group, corresponding to hyperplane arrangements of Coxeter type B. And in there as well, there are shards. They are a little more complicated, but they exist. The shards have a forcing relation. It's a little bit more complicated, but it works out. And for each of those shards, we were able to construct shard polytopes. There again, they're a little bit more complicated, but they work out. So whenever we have a lattice congruence on the lattice of regions of that arrangement that retains a certain upper set of shards, then we can again just sum up the shard polytopes for all the shards in that upper set and obtain a quotient hope for that congruence on the type B Coxeter arrangement, where the regions are not labeled by standard permutations anymore, but by signed permutations. And the hyperplanes, in addition to exchanging coordinates, some of them exchange the sign of one of the coordinates. But it's again an arrangement where the combinatorial structure is rather well known. And of course, it's interesting to see if we might be able to construct shard polytopes and therefore quotient hopes for other arrangements. It's known that every simplicial arrangement has a poset of regions that is a lattice. And so it might also allow the construction of shard polytopes in a similar way. These two types we worked with were the most easy because they were, well, combinatorially well understood. But whenever you have a more complicated arrangement, we showed that it is not necessary to construct a quotient hope from scratch, not to construct the quotient hope as a whole directly, but it's easier to find suitable polytopes for each of its shards, then sum them up, obtaining a suitable quotient hope with a nice quotient fan, which is exactly what we wanted to have whenever a lattice congruence removes some shards, retains some shards. So for other arrangements, I think a first step has been done. Thank you for listening.
Thank you. Do you have questions for Julian?
So type D does not work.
Type D, I wouldn't say that it doesn't work, but we have not yet succeeded in building shard polytopes for type D. Because again, the combinatorics is just one step more complicated than type B, so we haven't found shard polytopes in there yet.
Very beautiful talk.
Thank you.
Other questions? So in the chat, people are just congratulating you for the talk and for the figures. Those were amazing. Yes, I agree.
They're generated with the free open source math software Sage Math, if anyone is interested. This is how it's done.
Okay, so I guess there are no further questions. Thank you, Julian, again.